Has it ever worked?
I mean, sometimes. I just don't want to show you. You would get too, like, you wouldn't be able to teach your lesson. You'd get too surprised.
Alright, this final section in chapter 11 is about geometric sequences and series. So, arithmetic sequences, where we were adding the same term every time. Sequences are where we are multiplying by the same number every time to get the next term.
I don't like
so this term, this R is called the common ratio. Right. So we more often will use these formulas down here for common one. A sub n equals a sub 1 times r to the n minus 1 power. Right, where a sub 1 is the first, r is the number that we're multiplying by every time. Right? So I think these ones are actually a little bit easier than the arithmetic ones because there's only two pieces of ratio. Right? So on this first example here, we want to think about what number am I multiplying by every time. It is pretty obvious on this one that we're multiplying by 3 every time. What we can do to find the common ratio is take any term in the sequence and divide it by the previous term. Okay, so 27 divided by 9 is 3. 9 divided by 3 is 3. 3 divided by 1 is 3. Okay, but if you can just see it right off the bat, you don't have to go through that process. So to write the general equation here, we're just going to say a sub n equals the first term times the common ratio to the n minus 1 power.
It's just 1, and we just write it as 3 raised.
Yeah, if you don't have to write 1 times something. Yeah, so
I know this is like
the 1 is the first term?
Yeah, 1 is the first term. So I mean, if we're following this formula to the letter of the law, right, we would write 1 times 3 to the n minus 1, but 1 times anything is just that anything. Right? So, same thing here. Okay, we can say a sub n equals the common, or the first term, I guess, goes first. So the first term is negative 200 times the common ratio, which, yeah, again, this one almost obvious, right? We can see that we're cutting these terms in half each time, but if you don't see that right off the bat, just take a term and divide by the term before it. So negative 25 divided by negative 50 would be positive 1/2. Negative 50 divided by negative 100 would be positive 1/2. So we'll write that as 1/2 to the n minus 1 power. To write the formula, we will just leave it like that because if we're thinking about order of operations, we would have to raise this to the exponent, multiply. So we don't want to multiply the bases together. Less. Right. Other questions so far? Guys, go ahead and try C and D real quick here. Find the common ratio and use that to write the general.
Yeah. Why would you ever multiply something like that? That's horrible. I hate example D. That's all I've learned.
Dude, I don't know how you do D.
I didn't put on any lotion.
case of making it firm fast, that's not like the number. Let the record show nothing on
It's an approximation.
Did we get these for our general terms?
I'm sad to say that I did.
Why are you sad to say?
I can't tell you.
Questions? Alright, the next example, we just want to find a certain term in the sequence.
Oh yeah.
To do that, we're going to need to write our rule, just like we just did. So we're going to need to follow the pattern, a sub n equals a sub 1 times r to the n minus 1 power. So here, my rule will be a sub n equals, they tell me the first term is 10, and then my common ratio is 1.2 raised to the n minus 1 power. So if I want the 23rd term, I'm just plugging 23 in for n. So a sub 23 is going to be 10 times 1.2 raised to the 23 minus 1 power. So obviously we'll need a calculator for this. So what do we get for the 23rd term here? 552 point, what was it? 0614. All right, let's say we'll go to 3 decimal places.
Wait, just. I forgot that you guys multiplied by 10, and I was just looking at 1.2 to the 22nd, and I was confused.
Okay, go ahead and try B real quick here. First term is 17,714,700.
Oh yes, fine. I'm fine with that.
Yeah, I think that's pretty equivalent, right?
That's not that big of a number. I actually use that number quite a bit. Thank you.
So what do we get here?
My hair looks greasy when I put in this hair gel. Your hair is just always greasy.
What do we get for our answer here?
Put gel.
100? So, one observation to make here. Whenever my common ratio is less than 1 or greater than negative 1, my numbers are going to be going down. Okay? My common ratio is between negative 1 and 1. In this case, we have 1/3. My values are going to be decreasing in my sequence. All right? Questions? All right, so on example 3 here, we want to find the number of terms in this sequence. So again, we're going to have to use our formula. A sub n equals a sub 1 times r to the n minus 1 power. We can get a lot of information out of what we have here. So I know my first term is 4. Now my a sub n, we're saying, is the final term, right? So my a sub n is going to be 1 over 64. What's my common ratio? 1/2. And I'm multiplying by 1/2 every time to get the next term. Remember, another way to do that is to take any term and divide by the term before it. So if I plug all of that information in here, I'll have 1/64 equals 4 times 1/2 to the n minus 1 power. I want to solve this equation for n. To do that, I first want to get rid of this 4. So I'm going to divide both sides by 4, or that would be the same as multiplying by 1/4. Right? So 1/64 divided by 4 would be 1/256.
Yes. How'd you know that so quick?
I just did 64 times 4.
I wish I could be as good as you, Mr. Fetch.
I just break it down. 60 times 4 is 240. 4 times 4 is 16. 240 plus 16 is 256. How do I solve something like this? If I have my variable in my exponent,
Oh, do we have to do the
I have to do
The log.
or something.
yep,
Oh my god.
whenever we have a variable in an exponent, to solve that, to bring the exponent down, we need to use a log.
why? But why?
There's no other way to get the exponent down. So what do I need to do here?
Die.
I mean, I don't want it.
I'm sorry, that was the wrong answer.
What do I need to do?
Log. Start
Oh
with
wait,
second
is it
log.
We're not going to use. So
Log base 1.
So yeah, we're gonna use a lazy 7 here. We want to rewrite this as a log. Okay. Now, to use lazy 7, we usually had it written like this, right? We had the exponential on the left and the value on the right. So we're gonna say log base 1/2 of 1 over 256 equals n minus 1.
I can see clear.
Now this we can put in the calculator. Do we remember how to get to that button on the calculator? Nope. Math, and then I believe it's A. So you scroll all the way down, you get to log base, and you can put in half for your base, 1 over 256 inside of the log. So we get 8 equals n minus 1. Add the 1 over, and we get 9. So our answer is that there are 9 terms in this geometric sequence. Okay? Whenever we have a variable in the exponent, we need to use a log to solve. Okay?
Good thing that was simple.
I knew we were going to use log.
Questions on that? Alright, then on the back, let's talk about finding the sum of a geometric sequence. Okay, so just like our arithmetic sequences, we could add them all up. We have a nice formula for that. So our arithmetic formula was this. S sub n equals n over 2 times a sub 1 plus a sub n. Our geometric sum looks like this. Okay? A sub 1 times the quantity 1 minus r to the n over 1 minus r. Right? So if we have something in this form, we can pick out all of those pieces. Okay? This is my rule. So my rule is in the form of what we talked about on the front. A sub 1 times r to the n minus 1 power. And yeah, in this case, they're just using I as the variable. Right? So, to use this formula, my first term is going to be 5 in this case. Right? Now, I should put a disclaimer in here. If this value is not 1, which could happen, all we would do is plug this value into the formula to get our first term. Right? So if I plug this in, I'll get 5 times 0.7 to the 1 minus 1 power. So 0.7 to the 0 power is 1. 5 times 1 is 5. So plugging in this value gets me my first term. As long as this value is 1, this will be the first term, because this will be something to the 0 power. Okay? So my formula, my first term is 5 times 1 minus r, which is 0.7, to the n power. Okay, well, n is the number of terms. So in this case, going from 1 to 15, we will have 15 terms. So that'll be to the 15th power over 1 minus r. So we just need to plug all of that into the calculator to get the sum of the first 15 terms in this sequence. So what do we get for that? Say it again. 5875. So if we're going to 3 places, we'll do 16.588. Yeah, that's the answer. Right? We're just using this formula and getting each of those pieces.
We don't have to remember that, do we? Formula?
I don't know, let me think about it. He asked if you have to memorize that formula.
Those chapters. Wait, will we have to memorize any of them? Or will you just put them all?
Oh, for the
You should just put
For
them
the
there.
text.
oh yeah.
You should just put them all there.
I'll
There's
think
a lot
about
of
that.
I'll give you $1 and a picture of my brother.
I'll
You already
give
gave me the
you,
picture of your brother.
And $1. I'll give you a picture of my dad.
I'll give you a
Okay, so-
calendar with something on it.
The last idea here is the sum of an infinite sequence. It's not infinite.
Dang it.
If my common ratio is between -1 and 1. Okay, so they write it as the absolute value is less than 1. This means the same thing as r is between -1 and 1. If that's the case, and I add up an infinite number of terms, I will get a finite value. Okay, as long as my numbers are decreasing in value, and I add up an infinite number of them, I will get a finite value. The formula for that is actually very, very simple. It's just the first term over 1 minus the common ratio. Okay, so what we have to make sure of is that our r value is less than 1. So in this case, I go 2, 3 halves, 9 eighths, 27 30-seconds. So what would my r value be? How'd you get that? Yeah, you can do 9 eighths divided by 3 halves, or you can do 3 halves divided by 2. Okay, because on this one, it's not immediately obvious what you're multiplying by, right? So in this case, it probably would make sense to take a term and divide by the one before. So we get r equals 3/4. That is a value in between -1 and 1. So if I add all of these numbers up to an infinite number of terms, I will get a finite value. So my sum, my infinite sum, is going to be the first term over 1 minus the common ratio. So 2 divided by the fourth is 8. I can add these numbers up forever.
I understand.
Well,
You want to technically eventually get up there and higher than
it's the idea of an asymptote. If we continue to add these numbers up, we're going to get closer and closer and closer and closer to 8. It's basically it's an asymptote. Is the easiest way to describe this idea. Yeah, just like we have some function like 1 over.
So you can only do it because it's decreasing.
Exactly. We can only do it
It's only
because
getting
it's
smaller
decreasing.
and you only get so small.
Right. We're just adding a smaller number every single time. So it's, I mean, just like if we had a function like this and we graph it, there's an asymptote, right? We're getting closer and closer and closer to a value, but never actually reaching it. So, yeah, let's try this one real quick. So what would my common ratio be here? 2/3, right? Just take a term, divide by the one before. So that is between -1 and 1, so I can add up an infinite number of these. And that'll just be 3 divided by 1 minus 2/3. So 3 divided by 1/3 is 9. So I can add these terms up in this sequence forever, and they will add up to 9.